The universe is not just vast, it is incomprehensible. We say numbers like billions and trillions. We talk about light years and cosmic ages, but deep down our brains are not wired to understand them. They roll off the tongue as statistics, but the scale they represent is so far beyond anything in daily life that it might as well be another language. And yet, the more we learn, the more those numbers transform from cold facts into something else, a mirror that reflects back the fragility of our existence. When you hear that the observable universe stretches 46 billion light-years in every direction, your mind may try to process it, but your heart feels something deeper, a strange mix of awe and insignificance, fear and exhilaration. It is one of those truths that reshapes the way you see everything else, not because you suddenly understand the cosmos, but because you realize how little you ever did. For most of human history, the sky was a mystery. Ancient stargazers stood beneath the dark vault and thought the stars were lanterns or deities scattered across a dome that encircled the earth. The cosmos was small, understandable, contained. Then came the philosophers and early scientists, each daring to suggest something bigger, that Earth was not the center, that the sun was just another star, that the universe might stretch farther than anyone could imagine. With each revelation, the ground beneath our feet shifted, and what once felt infinite was revealed to be only a beginning. What makes these discoveries so powerful is not just their scientific accuracy, but their emotional weight. They tear away illusions of centrality and control, reminding us that we are not the measure of all things, but a flicker in an ocean of existence. And yet, this does not diminish us. In a strange, almost paradoxical way, the bigger the universe becomes, the more precious life feels. To know that stars live and die, that galaxies collide, that black holes swallow even light, and yet somehow, here on this tiny blue planet, molecules arrange themselves into consciousness, into you, sitting here breathing, listening. That realization is staggering. It is not just about physics or astronomy, it is about perspective. When you stare up at the night sky, you are not simply seeing light from distant suns, you are glimpsing history. Some of the photons striking your eyes tonight began their journey millions, even billions of years ago, long before Earth took its current form. To look up is to become a time traveler, to brush against the immensity of ages past, to feel the weight of eternity pressing softly on your awareness. This introduction is not meant to drown you in statistics or abstract theories. It is meant to open a door, to prepare your mind for the journey ahead, where every step takes you further from the comfort of the familiar and deeper into the strangeness of reality. The universe is not just big, it is layered with mysteries. Dark matter shaping galaxies, dark energy tearing them apart, quantum foam bubbling at the foundations of space, higher dimensions curling invisibly around us. These are not distant, irrelevant curiosities. They are the scaffolding of reality itself, the unseen framework that allows you to sit here and wonder at all. So, as we begin, take a moment to breathe. Feel the ground beneath you. Know that the atoms making up your body were forged in ancient stars, scattered by explosions older than Earth itself. You are already part of this story. You are already woven into the cosmic web, a fleeting but extraordinary voice of awareness in a universe that, for billions of years, existed without anyone to notice it. Tonight, we push past the edge of ordinary thought. Tonight, we ask questions so large they can only be answered with silence, questions that dissolve ego and replace it with wonder. This is not just science. This is not just philosophy. This is the oldest human instinct, to look up, to imagine, to feel small, and yet to feel connected. Welcome to the beginning of the journey. There is something timeless about the act of looking at the night sky. Long before telescopes, Long before electricity washed the stars away with city lights, human beings would lie back on the earth and see the heavens in their raw brilliance. The Milky Way, unbroken and unpolluted, spilled across the black dome like a river of fire, a sight so overwhelming that myths and stories naturally formed around it. To the Greeks, it was milk from the breast of a goddess. To the Mayans, it was a celestial road. To countless other cultures, it was a bridge between the world of the living and the realm of the divine. In every corner of the world, those who stared up at the stars saw not random points of light but patterns, constellations and narratives that gave meaning to the void. These early stargazers may not have had the mathematics or instruments to measure distances, but they had awe, and awe is what begins every great journey of discovery. The oldest records of astronomical observation, from Mesopotamia and Egypt to China and India, show a meticulous attention to the sky. Priests and scholars recorded the motions of planets, the cycles of eclipses, and the rising and setting of certain stars that marked the changing of seasons. To them, the heavens were not just beautiful, they were practical. They told farmers when to plant, sailors when to travel, rulers when to wage war. Astronomy was inseparable from astrology, and the belief that the stars controlled destiny gave them even greater weight. But hidden within this early mysticism was the seed of science, because every time someone charted the heavens with greater precision, the possibility of seeing them not as omens, but as natural phenomena grew. The moment humans began measuring the sky instead of merely worshipping it, the universe started to expand, not physically, but in the human mind. The Greeks pushed this further. Philosophers like Anaximander speculated that the earth might not be the center of all things, while Aristarchus even suggested that the sun, not earth, was the true anchor of our world. His ideas were too radical for the time and were ignored for centuries, but the seed was planted. Ptolemy's geocentric model, with Earth at the center and everything else revolving in perfect circles, became the official cosmic map for over 1,000 years. It was elegant, intuitive, and wrong. Still, it satisfied the need for order, and for most people the sky remained a ceiling, a fixed dome decorated with lights. To imagine otherwise was not only confusing but dangerous. What is striking about this period is not how wrong people were, but how their errors reveal just how difficult it is to let go of human-centered thinking. To the naked eye, the stars do look fixed. The sun does seem to rise and set around us. Common sense suggests a small universe in which we play the starring role. It took extraordinary persistence, courage, and imagination to challenge that view. The transition from myth to measurement, from Earth at the center to Earth as just another world among many, marks one of the most profound shifts in human thought. And it all began with those quiet nights of stargazing, with that simple but relentless question, what is out there? This is why Section 1 matters. It is about the emotional and intellectual groundwork, the first step humanity took on the ladder that would eventually reach galaxies, black holes, and the edge of the observable cosmos. Without that initial awe, without those early stories, there would have been no reason to measure, no hunger to discover, no willingness to endure centuries of mistakes just to inch closer to the truth. When you stand beneath a dark sky today and feel your breath catch at the sight of the Milky Way, you are sharing the same experience that shaped the first astronomers. Their tools were crude, their theories often flawed, but the feeling, the mixture of fear, wonder, and smallness, was exactly the same as yours. And that is the true beginning of cosmic discovery, not in numbers, but in the raw, unfiltered awe of being a conscious creature under a sky too big to understand. For countless centuries, the stars were fixed jewels in the sky, brilliant yet unreachable, their distances unknowable. People could measure their patterns, track their rising and setting, even predict eclipses, but the actual scale of the heavens remained a mystery. How far away were those tiny points of light? Were they just close sparks or vast worlds? The imagination ran wild, but imagination alone could not pierce the distance. It wasn't until the 19th century that humanity finally developed the tools and patience to measure for the first time the true distance to a star. That achievement changed everything, because once you put a number on the stars, the universe ceases to be an abstract dome and becomes a physical, measurable space. Suddenly, the cosmos had depth. The breakthrough came through the concept of parallax, a simple but powerful idea. Hold out your thumb in front of your face and look at it first with one eye, then the other. Notice how your thumb seems to jump against the background. That shift is parallax, and the closer an object is, the bigger the shift appears. Early astronomers realized that if they could detect a similar wobble in the stars as Earth moved around the Sun, they could calculate how far away those stars truly were. The problem was that stars are so unimaginably distant that their shifts are minuscule, smaller than the width of a human hair seen from miles away. For centuries, telescopes were simply not precise enough to measure it. The idea was there, but the technology wasn't ready. Then came Friedrich Bessel in 1838, using a new instrument called a heliometer, designed to make incredibly fine angular measurements. Bessel chose a relatively nearby star, 61 Cygni, a faint but fast-moving object in the night sky. He tracked it obsessively for months, recording its tiny movements against the fixed background of more distant stars. Finally, he detected it, a shift so small, just a fraction of an arc-second, but real. From that tiny measurement, he calculated the distance over 10 light-years away. 10 light-years may not sound like much today, but to the people of that era, it was revolutionary. For the first time, a star had a real measurable distance. The night sky was no longer painted on a ceiling. It was a three-dimensional space, stretching farther than the imagination had ever dared. Others followed quickly. Thomas Henderson measured Alpha Centauri, the nearest star system to us, while Wilhelm Struve measured Vega. Piece by piece, the distances began to build, and with each new number, the scale of the universe expanded in the human mind. No longer were the stars close sparks, they were suns like our own, so distant that even light, the fastest thing in existence, took years to bridge the gap. The cosmos was suddenly enormous, and humanity was suddenly small in a way it had never been before. But perhaps the most profound shift wasn't just scientific. It was emotional. Imagine living in a world where the sky was thought to be a ceiling only a few miles above you, and then learning that those twinkling lights were not just farther than mountains or oceans, but farther than you could possibly travel in 1,000 lifetimes. It was like discovering that the world you lived in was not a room, but a vast ocean, and you were floating on a raft in the middle of it. That sense of distance, that realization of depth, was the first great step in humanity's confrontation with cosmic scale. From there, the cosmic ladder would only grow taller. Cepheid variable stars, supernovae and redshifts would take us further and further into the abyss. But it all began here, with a man patiently measuring a faint star and daring to believe that the universe could be quantified. It was the first time humanity put a number to infinity, and in doing so, cracked open the door to everything that would follow. By the early 20th century, humanity had learned to measure the distances to nearby stars, but the bigger question remained unresolved. What were the faint, cloudy patches that dotted the night sky, the so-called nebulae that telescopes revealed in spiraling or fuzzy forms? Were they small gas clouds within our own Milky Way, or were they something far more dramatic? Entire systems of stars, separate galaxies lying far beyond our own. The debate was fierce, known as the Great Debate between astronomers Harlow Shapley and Heber Curtis in 1920. Shapley believed that the Milky Way was the entire universe and that these mysterious nebulae were simply local phenomena within it. Curtis, however, argued that these were island universes of their own, galaxies as large or larger than the Milky Way, scattered across a much greater cosmos. At the time, no one had the evidence to prove either view, and the question lingered like a haunting mystery at the heart of astronomy. The answer came from the work of Edwin Hubble at Mount Wilson Observatory, where the largest telescope of the time, the 10-inch Hooker telescope, was trained on the Andromeda Nebula. Hubble used Cepheid variable stars, a special kind of star whose brightness pulses at a regular rhythm. The remarkable discovery made by Henrietta Swan Leavitt earlier in the century was that the period of these pulsations was directly related to their intrinsic brightness. By measuring how long it took a Cepheid star to brighten and dim, astronomers could determine its true luminosity, and by comparing that to how bright it appeared from Earth, they could calculate its distance. Cepheids became cosmic yardsticks, the second rung of what would later be called the distance ladder. When Hubble identified Cepheid variables in the Andromeda Nebula in 1923, he performed the calculation and found something astonishing. The stars were far too distant to be inside the Milky Way. In fact, they lay more than 2 million light-years away, proving that Andromeda was not a local cloud, but an entire galaxy of its own, comparable in size to the Milky Way and filled with billions of stars. The universe had suddenly exploded in size. Overnight, humanity's cosmic home went from one galaxy to a universe filled with countless others. The Milky Way was not the whole of existence, but just one island among trillions. This realization was not just a scientific breakthrough, it was an existential earthquake. Imagine believing that your galaxy, vast as it was, contained everything that existed, and then learning that it was only one of many. The scale of the cosmos was once again multiplied beyond comprehension, and with it came the humbling recognition of our smallness. Earth was not just a planet circling an ordinary star in a galaxy filled with stars. It was now part of an ocean of galaxies stretching out as far as the eye could see, each one a Milky Way of its own, each one potentially with planets, with life, with stories unfolding far beyond our reach. Hubble's work did not stop there. By comparing the distances to galaxies with their spectral redshifts, the stretching of light toward the red end of the spectrum as they moved away, he discovered that galaxies were not static. They were racing away from us, with speed increasing the farther they were. This was the discovery of the expanding universe, a revelation so profound that it changed not only astronomy but all of science. Space itself was stretching, carrying galaxies with it, a discovery that gave birth to the concept of the Big Bang and the modern picture of cosmology. Section by section, humanity's view of the cosmos had grown larger, first with the realization that stars were distant suns, then with the proof that nebulae were other galaxies, and finally with the discovery that even these galaxies were not fixed but part of an expanding universe. Each step tore away another layer of illusion, each one forcing us to confront the staggering immensity of reality. And yet, with every increase in scale, the same feeling returned: awe, humility, and a sense of wonder that somehow, from within this vastness, we are able to ask the questions that reveal it. Once the realization set in that the universe was expanding, astronomers naturally assumed that gravity, the great universal force of attraction, would eventually slow it down. The picture was simple and elegant. The cosmos had exploded outward in a great beginning, but over billions of years, the pull of matter would tug at the expansion. Depending on how much matter the universe contained, it might slow to a crawl, it might balance perfectly and coast forever, or it might even reverse into a catastrophic collapse, the so-called Big Crunch. For decades, this was the accepted view, the central cosmic question being not whether the universe would end, but how. Yet as scientists sought more precise answers, they needed more reliable tools to measure distance across the depths of space. Parallax and Cepheid variables were useful, but they had limits. Beyond a certain scale, the stars themselves were too faint to resolve. What was needed was something brighter, more dramatic, something that could serve as a beacon across billions of light years. The universe, it turned out, provided just such a tool. Type 1a supernovae. A Type 1a supernova is not the explosion of a massive star like the familiar core collapse supernovae, but rather the violent death of a white dwarf star. These small, dense remnants of stars are like cosmic embers, often existing in binary systems where they slowly steal material from their companion stars. As the white dwarf absorbs this stolen matter, it grows heavier until it reaches a critical mass known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. At that moment, the star can no longer support its own weight, and it detonates in a cataclysm so bright it outshines an entire galaxy. What makes Type 1a supernovae so valuable to astronomers is their remarkable uniformity. Because they all explode at nearly the same mass, they all reach nearly the same peak brightness. In other words, they are standard candles, cosmic flashlights, whose true luminosity is known by comparing how bright they appear from Earth to how bright they should be. Astronomers can calculate their distances with astonishing precision. Using these stellar explosions as markers, scientists began charting the expansion of the universe on scales never before possible. In the 1990s, two independent teams set out to measure the fate of cosmic expansion by observing distant Type 1a supernovae. The expectation was simple. They would find evidence that the expansion was slowing under the influence of gravity. But what they discovered shook the foundations of cosmology. The faraway supernovae were dimmer than they should have been if the universe was slowing down. The conclusion was unavoidable. The expansion of the universe was not decelerating, it was accelerating. This discovery was as shocking as it was unsettling. Something unknown was counteracting gravity, pushing galaxies apart faster and faster as time went on. Astronomers gave it a name, dark energy, not because they understood it, but because they did not. This mysterious force, invisible and intangible, now dominates the evolution of the cosmos. Current estimates suggest that nearly 70% of the total energy content of the universe is dark energy, while ordinary matter, the stuff of stars, planets, and people, makes up less than 5%. The rest is dark matter, itself poorly understood, but gravitationally essential. The cosmos, it turns out, is built mostly of things we cannot see and cannot fully explain. The emotional weight of this revelation is profound. For centuries, humans believed that the universe was slowing down, winding toward an eventual halt or reversal. Now we face a stranger possibility, a runaway cosmos, one that grows emptier and lonelier with every passing eon. Galaxies are already slipping away, carried beyond a cosmic horizon from which their light will never return. Billions of years from now, distant stars will vanish from view, leaving only the local group of galaxies bound together by gravity. Beyond that, even those remnants will dissolve into the dark. The accelerating expansion writes a future not of fire or collapse, but of silence. And yet, even in that silence, there is wonder. To live in the moment when this discovery was made is extraordinary, a reminder that the universe is not finished surprising us. The cosmos is not static, not predictable, not even fully comprehensible. It evolves in ways that defy intuition, leaving us to stand beneath the night sky with more questions than answers. We are witnesses to an unfolding mystery, one that redefines our place in the grand story of existence. The revelation of acceleration is not just a scientific milestone, it is a reminder that the universe is stranger than we imagine, and stranger still than we can imagine. When the term dark energy was first proposed, it was not meant to describe something understood, but rather to label an enigma so vast that even the name was a placeholder for ignorance. What is it that drives the acceleration of the universe? Why does space itself seem to create more space, stretching faster the more it expands? The answers remain elusive, but the implications are staggering. Unlike matter, which clumps together under gravity, dark energy does not gather in stars or galaxies. It does not glow, it does not pull, it does not slow. Instead, it acts as a kind of anti-gravity, a pressure that pushes outward, making the universe larger with every passing second. To understand dark energy is to face the reality that most of what determines the fate of the cosmos is invisible, untouchable, and almost certainly beyond our everyday comprehension. Today, scientists estimate that nearly 70% of the energy content of the universe is dark energy. Ordinary matter, the atoms that make up you, me, stars and galaxies, comprises less than 5%. Dark matter, another unseen substance that provides the gravitational scaffolding for galaxies, adds about 25%. That means the vast majority of the cosmos is made up of something we cannot see and do not fully grasp. Imagine standing in a room and realizing that everything you can touch and measure, every object, every particle, accounts for only a tiny fraction of what is actually there, while the rest exists in forms you cannot perceive. That is the reality of our universe. The discovery of dark energy did more than rewrite textbooks. It forced scientists to reconsider the destiny of everything. If expansion is accelerating, then the galaxies beyond our local cluster are already slipping from view, and the future holds a universe in which distant lights fade away forever. The possibilities are unsettling. One scenario is the so-called heat death, in which galaxies, stars, and eventually even atoms drift so far apart that no meaningful interaction is possible. Over trillions of years, the universe would grow colder and quieter until nothing remains but thin radiation in a void too vast to measure. Another possibility is the Big Rip, in which dark energy grows stronger over time, eventually overpowering all forces of nature. In that scenario, galaxies would first be torn apart, then solar systems, then planets, and finally even atoms themselves would be ripped into subatomic shreds by the relentless expansion. These are not distant science fiction imaginings, but plausible outcomes, each dependent on the true nature of dark energy, which we still do not know. Some theories suggest dark energy is a property of space itself, a cosmological constant first hinted at by Einstein and later abandoned. Others propose it may be a dynamic field that changes over time, something woven into the very fabric of space-time. Some even speculate it might decay, reverse, or behave in ways we cannot yet imagine. Each possibility leads to a different cosmic future, from endless expansion to collapse, to cycles of rebirth. At present, no observation has revealed the answer, and so the question lingers like a shadow across all of cosmology. For those who seek comfort in permanence, dark energy offers none. It tells us the universe is not a stable stage, but a shifting, evolving phenomenon whose story is still unfolding. And yet, within that uncertainty lies a kind of strange beauty. To live at this moment in cosmic history, when the acceleration is first being discovered, is to stand at a threshold billions of years from now. Future civilizations, if any survive, may find themselves locked in a shrunken horizon, where only local galaxies are visible, unaware of the vast universe that once existed beyond. but we right now can see it. We are witnesses to the truth of an expanding, accelerating cosmos, a truth that will vanish from view as the universe ages. This knowledge does not lessen us, it elevates us. It shows that we are not passive inhabitants of a static universe, but conscious observers at a moment of revelation. Dark energy may be unknowable for now, but the very act of seeking to understand it proves something profound about us. Against the immensity of time and the inevitability of cosmic silence, we continue to ask questions, to reach for answers, to confront the mysteries that shape our destiny. And in that reaching, perhaps we find the closest thing to meaning that the universe will ever give. Once the reality of expansion and acceleration set in, astronomers turn to an even deeper question. What is the shape of the universe? At first glance, this might seem like a simple matter of geometry, but the stakes are far higher than lines on paper. The shape of the cosmos determines not only how space is structured, but also how time unfolds and how the universe will ultimately end. For centuries, humans assumed the universe must be infinite and flat, stretching out endlessly like an infinite plane. But physics demanded a closer look. Einstein's theory of general relativity showed that space is not a rigid backdrop, but a flexible fabric that can curve under the weight of matter and energy. Depending on how much matter the universe contains and how dark energy behaves, the cosmos could take on one of three possible shapes: closed, open, or flat. A closed universe can be imagined as the three-dimensional surface of a sphere. It has no edge, but if you travel far enough in one direction, you would eventually loop back to where you started. In this model, the gravitational pull of matter would eventually slow expansion and reverse it, leading to a final collapse known as the Big Crunch, where everything is pulled back into a fiery convergence. It is a universe that ends not in silence but in fire, a mirror image of the Big Bang. A cosmic inhale after a cosmic exhale. Some thinkers even imagined that this collapse could trigger another explosion, suggesting a cyclic universe, an eternal sequence of bangs and crunches, a cosmos without a true beginning or end. An open universe, on the other hand, resembles the shape of a saddle or hyperbola. It curves outward, expanding forever without bound. In this scenario, galaxies continue to drift apart, and expansion never slows enough to reverse. The cosmos becomes infinite in size, but also infinitely lonely, as matter thins out and stars eventually die, leaving behind only the cold debris of a once vibrant creation. This open model points toward a bleak future, a slow fade into nothingness, where the universe becomes an endless desert of scattered particles. Then there is the flat universe, like an infinite sheet of paper. Expansion continues forever, but balanced delicately between collapse and runaway acceleration. For decades, scientists debated which of these shapes best described reality, and the answer came not from speculation but from a faint glow in the sky, the cosmic microwave background, the afterglow of the Big Bang itself. Precision measurements by satellites like WMAP and Planck revealed that the geometry of the universe is astonishingly close to flat, with only the tiniest margin of deviation. To the best of our knowledge, space does not curve noticeably on cosmic scales. Instead, it stretches out in every direction as far as we can see, not bending back on itself, not curving outward into a saddle, but extending like an infinite horizon. At first, the idea of a flat universe might seem comforting, as though it was stable and unchanging. But when combined with the reality of dark energy, flatness carries its own haunting implications. A flat, accelerating universe means expansion continues not just endlessly, but ever faster. Over time, more and more galaxies will slip beyond the cosmic horizon, vanishing from view forever. The night sky will grow darker, not because stars die, but because their light can no longer reach us. Eventually, Only the local group of galaxies, bound together by gravity, will remain visible, while the rest of the cosmos disappears into an unreachable abyss. It is a universe where loneliness grows with every passing eon, where silence is not just a possibility, but an inevitability. The strange irony of cosmic geometry is that it reveals destiny. A closed universe leads to fire, an open universe to endless cold, a flat accelerating universe to vanishing horizons. Each possibility carries a different emotional weight, a different vision of the future. And yet, despite all our measurements and theories, the ultimate truth remains hidden. Dark energy may shift over time, changing the fate of everything in ways we cannot yet predict. The universe may seem flat now, but its story is not finished. This uncertainty is part of what makes the question so powerful. To ask about the shape of the universe is not just to ask about geometry. It is to ask about beginnings and endings, about what lies beyond the limits of sight and what awaits when the last star fades. We live in a cosmos where even space itself has a personality, curving, stretching, shaping destiny. And though we do not yet know the final act, we know enough to understand this. The shape of the universe is not just a backdrop to our existence. It is the stage, the script, and perhaps the last line of the story. In the beginning, after the Big Bang's blinding light had cooled and the universe settled into a long dark age, there were no stars, no galaxies, no familiar structures at all. For nearly 400 million years, the cosmos was filled with a thin fog of hydrogen and helium, drifting silently through expanding space. Gravity worked patiently, pulling matter into clumps, but the universe remained starless, a vast ocean of potential without a single spark. Then, in that darkness, something extraordinary happened. The first stars were born, and with them, the universe lit up for the very first time. These stars were unlike anything we know today. Astronomers call them population 3 stars, the hypothetical first generation forged from pure primordial gas, with no heavy elements, only hydrogen and helium. They were monsters, massive, unstable, brilliant giants burning hotter and faster than almost any star we can observe now. Because they were so large, often hundreds of times the mass of our sun, these early stars lived brief, violent lives, where our sun will shine steadily for billions of years. Population 3 stars burned out in only a few million, some in mere hundreds of thousands. They ended their lives not with quiet fades, but with cataclysmic explosions, supernovae that blasted the first heavy elements into the void. Before these stars, there was no carbon, no oxygen, no iron. The universe was chemically barren, incapable of forming planets, oceans, or life. It was only through the fiery deaths of these early giants that the raw ingredients for everything familiar were created. Every atom of carbon in your body, every molecule of oxygen in your lungs, every trace of iron in your blood was forged in the hearts of those stars and scattered into space when they died. In a very real sense, they were the universe's first alchemists, transforming simple hydrogen into the complex elements that would one day build worlds. What is haunting is that we have never actually seen a population 3 star. They lived too long ago, too far away, and their light has long since faded. Yet we know they must have existed, because their chemical fingerprints linger in the generations of stars that came after. The oldest stars we can observe today, ancient red dwarfs in the Milky Way's halo, carry traces of heavy elements that could only have come from earlier stellar explosions. Their existence is evidence, the echo of a first generation long vanished. Some astronomers dream that perhaps one or two of these primordial giants, if small enough, might still survive somewhere in the cosmos, dim and ancient, a relic from a time before planets, before galaxies, before everything we know. But if they are gone, then their legacy remains etched in us, in the chemistry of life, in the dust of every rock and drop of water. The birth of the first stars was more than just a physical transformation. It was a turning point in the story of existence. Light returned to the cosmos after ages of darkness, and with it came structure. Clumps of stars drew together under gravity, forming the earliest galaxies, chaotic and irregular at first, but growing larger and more organized with each collision and merger. The cosmic web began to take shape, filaments of matter stretching across billions of light years, punctuated by glowing knots of stars. What began as a universe of silence became a universe of brilliance, sculpted by fire and collapse, by creation and destruction. To imagine these first stars is to picture a sky unlike any we have ever seen. No faint pinpoints scattered in the dark, but colossal beacons blazing so brightly they outshone entire galaxies. Their light cut through the hydrogen fog, reionizing the universe and allowing photons to travel freely, making the cosmos transparent for the first time. In their short, furious lives, they set everything in motion: the chemistry of life, the formation of galaxies, the long chain of stellar generations that would eventually give rise to planets and consciousness. Without them, the universe would still be dark and lifeless. With them, the stage was set for everything to come. The first stars remind us of something profound, that creation often requires destruction. Their brilliance was inseparable from their fragility, their gift inseparable from their doom. They burned fast and died young, but in their deaths, they seeded the universe with possibility. We are here because they were there, because hydrogen and helium learned how to become more, because light returned to the darkness. And though we cannot see them, though their brilliance belongs to a time so distant it feels mythical, every breath you take is a whisper of their legacy. After the first stars burned and died, the universe entered a new era, one defined not just by isolated bursts of light, but by the gathering of those lights into structures grand enough to reshape everything. Gravity, the quiet sculptor, began weaving stars into patterns, drawing them together into clusters that over millions of years became the earliest galaxies. These were not the elegant spirals we see in modern telescopes, but chaotic, irregular collections of stars, gas, and dust. They collided often, merging and tearing each other apart, yet with every collision they grew, becoming larger, brighter, more organized. What began as scattered sparks in the cosmic dark transformed into vast cities of stars, each one containing billions of suns. The galaxies were the universe's first architecture, the scaffolding upon which all future history would hang. As time passed, these galaxies did not remain isolated. They interacted with one another in slow, majestic encounters that unfolded over billions of years. Unlike our human sense of collisions, sudden, violent impacts, galactic mergers are dances. Stars within them are so far apart that they almost never collide directly, but their collective gravity distorts everything, stretching spiral arms, igniting bursts of star formation, and feeding the growth of black holes at their centers. The result is not destruction, but transformation. From two galaxies can come one larger, more massive structure, sometimes an elegant spiral, sometimes a bloated elliptical. The cosmos builds by combining, by gathering small things into larger things, until the vast tapestry of galaxies forms a network stretching across the observable universe. Our own Milky Way is a product of this process. It did not appear fully formed, but grew slowly through countless mergers with smaller galaxies. Even now, the process continues. The Milky Way is actively consuming its smaller neighbors, like the Sagittarius dwarf galaxy, whose stars are being stretched and torn into streams that wrap around us. These streams, faint rivers of starlight, are the fossils of past collisions, the lingering evidence that galaxies do not live alone, but constantly interact and change, and the greatest collision is yet to come. In about 4 billion years, the Milky Way and the Andromeda Galaxy will drift together and merge, their stars swirling into new patterns, their black holes spiraling into one. To an observer alive then, the night sky will be filled with arcs and streams of glowing stars, a spectacle of unimaginable beauty. And when the dance is complete, the two galaxies will become one enormous elliptical galaxy, perhaps called Milkomeda, a testament to the endless cycle of creation through collision. But galaxies are not just star clusters, they are ecosystems. Within their arms and halos, gas clouds collapse to form new stars. Stellar nurseries, lit by brilliant blue giants, dot their spirals like glowing embers. In between lie regions of dust and darkness, reminders that galaxies are not static portraits, but living, evolving systems. Some galaxies remain small and irregular, content to drift on the edges of clusters. Others grow massive, dominating their neighborhoods, shaping the space around them with their gravity. Together they align into filaments of the cosmic web, strands of light and mass that stretch across billions of light years. Between these filaments lie vast voids, regions so empty they defy comprehension, places where galaxies are rare and silence reigns. The result is a structure so immense that simulations of it resemble the neurons of a brain, as if the universe itself were a kind of cosmic thought. What is humbling is that galaxies, for all their size and majesty, are temporary. Star formation cannot last forever. The gas and dust that fuel it will eventually run out, leaving galaxies to fade into quiet collections of aging stars. And yet in their prime, galaxies are the forges of possibility. They give birth to stars, which give birth to elements, which give birth to planets, which give birth to life. To trace the story of galaxies is to trace the story of everything that has ever lived, because without these vast engines of creation, there would be no homes for suns, no nurseries for worlds, no stages for consciousness. They are not just distant patches of light in a telescope, but the very wombs of existence, the structures that made our presence in the universe possible. And so the galaxies remind us of something deeper. The universe does not grow by remaining still, but by colliding, merging, evolving. Order emerges from motion, beauty from chaos. Every spiral arm, every star-filled core, every faint stream of starlight torn from a smaller neighbor is part of a grander pattern, the constant reshaping of the cosmos itself. When we look at the Milky Way stretched across the night sky, we are not just seeing our home, we are seeing history, a story written in starlight, and a glimpse of the endless dance that continues even now. To the naked eye, the Milky Way appears as a faint band of light smeared across the night sky, a soft glowing river that has inspired myths and stories for thousands of years. Ancient cultures imagined it as a celestial pathway, the backbone of the night, a trail for spirits or gods. But when science turned its gaze to that ribbon of stars, it revealed something far grander. The Milky Way is not a path, but a galaxy, a vast spiral system stretching more than 100,000 light-years across, containing hundreds of billions of stars and cradling our sun in one of its quieter arms. It is our home in the cosmos, and yet we can never see it from the outside. We are forever embedded within it, like insects trying to map the forest while clinging to a single tree. The Milky Way is a barred, spiral galaxy, its arms curving gracefully outward from a central bar-shaped cluster of stars. Our solar system lies in the Orion Arm, a minor spur nestled between two larger arms, Sagittarius and Perseus. This placement is fortuitous because being away from the crowded galactic core gives us a clearer view of the universe beyond. If Earth had formed deep within the central bulge, where stars blaze in dense swarms and radiation fills the air, the sky might be breathtakingly bright, but the chance for a stable, life-supporting world would be far lower. In this sense, our quiet neighborhood is a gift, offering both stability and perspective. The entire galaxy rotates, though at a pace so slow it defies human intuition. Our sun, racing at nearly 800,000 kilometers per hour around the galactic center, still takes about 20-30 million years to complete a single orbit. The last time our solar system was in its current position along this path, dinosaurs walked the Earth. Every star, every system, is caught in this enormous dance, circling the unseen heart of the Milky Way. That heart, we now know, hides something both terrifying and fascinating. A supermassive black hole millions of times the mass of our sun, known as Sagittarius A. We cannot see this black hole directly, but its presence is undeniable. Stars near the center of the Milky Way whip around invisible points at staggering speeds, their orbits betraying the gravitational monster that anchors them. Occasionally, clouds of gas spiral inward, heating to incredible temperatures before vanishing into the event horizon, emitting bursts of radiation that ripple outward across the galaxy. Sagittarius A is relatively quiet now, but evidence suggests it has flared in the past, blazing brighter than it does today. Whether calm or active, it defines the galaxy's center, the dark heart around which everything else revolves. Yet the Milky Way is more than just stars and black holes. It is also made of vast clouds of gas and dust, nurseries where new stars are born. These regions, glowing as nebulae when lit by nearby radiation, are places of constant creation. Gravity squeezes hydrogen until nuclear fusion ignites, and a new sun bursts into life. Around these newborn stars, disks of dust swirl into planets, moons, asteroids, and comets. Every solar system, including our own, began in such a nursery, and as older stars die, some gently, others in violent supernovae, they enrich the galaxy with heavy elements, seeding future generations with the building blocks of life. The Milky Way is not static. It is alive with cycles of birth, death, and renewal. Surrounding all of this luminous matter is something stranger still, dark matter. Though invisible, it outweighs all the stars and gas combined, forming a vast halo that envelops the galaxy and holds it together. Without it, the stars on the edges of the Milky Way would spin away into space. Dark matter binds the spiral, gives it shape, and allows it to persist. We cannot touch it. We cannot see it. But without it, the galaxy could not exist. And so, when you look up at the Milky Way on a clear night, you are not just seeing a blur of stars. You are seeing a cross-section of our home, the edge-on view of a spiral so immense that light itself takes 100,000 years to cross it. You are seeing history written in starlight, from the ancient giants that seeded the galaxy with elements, to the young suns still forming in hidden clouds, to the faint streams of stars torn from smaller galaxies that the Milky Way consumed. You are seeing, in short, the story of everything we are a part of, and everything we owe our existence to. Amid the sprawling grandeur of the Milky Way, with its billions of stars, nebulae, and swirling arms, lies one star so ordinary that it would never catch your eye among the countless points of light. And yet for us, it is the most important star of all. Our sun, a modest yellow dwarf, formed around 4.6 billion years ago from the collapse of a dense region in a molecular cloud. This cloud, composed mostly of hydrogen and helium with traces of heavier elements from earlier supernovae, drifted silently until gravity nudged it inward. Over time, the gas collapsed into a rotating disk, its center heating and compressing until nuclear fusion began. A star was born, but the sun did not emerge alone. Around it, leftover dust and gas swirled, colliding and clumping into planets, moons, asteroids, and comets. It was from this chaos that Earth, our fragile blue world, was forged. The sun's role in this story cannot be overstated. It is not merely the light of our days, but the very reason life exists here at all. Its energy fuels everything from the growth of plants to the dynamics of weather. Without its steady warmth, Earth would be a frozen rock drifting through space. Yet the sun is not too large or too small, not too unstable or too faint. It burns in a sweet spot, long-lived and steady, giving life billions of years to emerge and evolve. Its position in the galaxy, too, is fortunate. Nestled in a quiet arm, away from the violence of the galactic core, it resides in a relatively stable environment, shielded from excessive radiation and catastrophic gravitational disruptions. These coincidences are not evidence of design, but of circumstance. Still, they remind us of how delicately balanced our existence truly is. From the start, the sun shaped the fates of the planets around it. Those too close, Mercury and Venus, were scorched by its intensity. Those too far, Jupiter, Saturn, Uranus, Neptune, remained cold and inhospitable, though they gained moons and rings of their own. Earth occupied the perfect middle ground, the so-called Goldilocks zone, where liquid water could persist. Early in Earth's history, when the planet was molten and violent, the sun's energy interacted with oceans and atmosphere to drive the chemistry that eventually gave rise to life. Every breath you take, every heartbeat, every movement is powered by energy that began in the sun's core, where hydrogen atoms fuse into helium, releasing light that takes thousands of years to escape before traveling across space to reach us. To live on Earth is to live on borrowed sunlight. And yet, for all its centrality to us, the sun is unremarkable. Among the billions of stars in the galaxy, it is just one more, neither the brightest nor the dimmest, neither the youngest nor the oldest. It does not blaze as a blue giant or shrink as a red dwarf. It is average, but that ordinariness is what makes it extraordinary. Because if something so typical can give rise to oceans, continents, forests, and minds capable of wonder, then perhaps the universe is filled with other suns cradling other worlds. Our sun is not a cosmic exception, it is a cosmic invitation, a hint that life may be written into the physics of stars themselves. The sun's future is already written in its core. With about 5 billion years of fuel left, it will continue to shine steadily for eons. But eventually it will swell into a red giant, swallowing Mercury and Venus, perhaps even Earth. Its outer layers will drift into space, forming a glowing nebula, while its core will shrink into a white dwarf, a faint ember of its former self. That end may sound bleak, but it is the natural cycle of stars, and from that cycle comes renewal. The elements scattered by dying suns become the seeds of new stars, new planets, new possibilities. The sun is part of that chain, born from the ashes of others, and destined to give its own ashes to the future. To think of the sun this way is to understand both our fragility and our connection. Every meal you eat, every step you take, is powered by a star that is ordinary in every sense except this. For us, it is everything. And in its ordinariness lies the most profound truth of all, that the miracle of life is not rare, not impossible, but perhaps inevitable, woven into the fabric of stars that burn quietly across the galaxy. For most of human history, we believed Earth was unique, the only world with oceans, continents, and the miracle of life. Even after astronomers realized the sun was just one star among countless billions, the assumption persisted that planets were rare and that life, especially intelligent life, was a cosmic accident. But in the last few decades, that assumption has been shattered. We now know that planets are not exceptional at all. They are everywhere. Orbiting almost every star we can see are worlds of all sizes and kinds, from gas giants to rocky spheres, from molten infernos to frozen wastelands. These discoveries have transformed our understanding of the universe and raised a question both exhilarating and haunting. If there are so many planets, how many might be like Earth? The first confirmed detection of an exoplanet came in the 1990s, and it was nothing like our world. Astronomers discovered giant gas planets orbiting perilously close to their stars, so hot that their atmospheres boiled away. These hot Jupiters were bizarre and unexpected, nothing like anything in our solar system, yet their very existence proved the point. Other worlds were real, and the universe was far more imaginative than we had dared to dream. From there, discoveries multiplied. Missions like Kepler and TESS revealed thousands of planets across the galaxy, each one tugging on its star or dimming its light as it passed in front. Suddenly, the night sky was not a backdrop of stars, but a sea of suns, each one likely with planets of its own. Among these thousands of exoplanets, some fall into what astronomers call the habitable zone, the region around a star where conditions might allow liquid water to exist. These are the so-called Goldilocks planets, not too hot, not too cold, but just right for life as we know it. Some are rocky, Earth-sized worlds orbiting stars surprisingly close to us, 40, 50, 100 light-years away, distances that are both unimaginably vast and cosmically near. With new telescopes, like the James Webb Space Telescope, we are beginning to study their atmospheres, searching for hints of water vapor, oxygen, or methane, chemical fingerprints that might betray the presence of biology. For the first time in history, we have the tools not just to imagine other Earths, but to detect them. Yet, with every discovery comes attention. On one hand, the sheer number of planets suggests that life might be common. If billions of Earth-sized worlds orbit billions of stars, then perhaps the cosmos is teeming with oceans, forests and creatures staring up at their own skies. On the other hand, the silence is deafening. We see no evidence yet of civilizations, no signals, no ruins, no obvious signs of intelligence. This paradox, known as the Fermi paradox, hangs over every new discovery. If the universe is full of planets, where is everyone? Are we alone, or are we simply too early, too far, or too primitive to detect them? The search for exoplanets does not just open scientific possibilities, it forces us to confront existential questions about our place in the cosmos. For now, we are still explorers on the shore, gazing across an ocean of possibility. Every new exoplanet discovered is a message from the stars that Earth is not unique, that worlds are common, and that life, if it exists elsewhere, may not be a fluke but a natural consequence of physics. Perhaps the nearest Earth-like planet is only a few dozen light-years away, close enough for us to dream of future journeys, yet far enough to remain untouchable with current technology. We may never set foot on these distant shores, but the knowledge of their existence already changes us. It tells us that the universe is not barren but fertile, not hostile but rich with places where life might bloom. And so the search continues, not only with telescopes, but with imagination. Each new discovery forces us to reframe our place in the universe, from the only world to one among many. Perhaps someday, with patience and technology, we will find a world with oceans, continents and skies that remind us of home. Perhaps one day, a spectrum of light from a distant star will reveal the unmistakable breath of alien life, and in that moment, Earth will no longer be the only voice in the cosmos. It will be one of many, part of a choir that has always been singing, waiting for us to listen. Finding planets is one thing, But the real question that burns behind every discovery is whether life exists beyond Earth. To search for life is not merely a scientific endeavor. It is a reflection of our deepest need to know whether we are alone. This search takes many forms, from looking at the chemistry of alien atmospheres to listening for faint signals that might reveal technology, and every approach is an attempt to answer the same timeless question: is biology a universal story, or is Earth a singular miracle? The first approach is to search for biosignatures, chemical markers that betray the presence of life. On Earth, our atmosphere is shaped profoundly by biology. Oxygen, for example, is unstable on its own. It constantly reacts with rocks and other elements. The reason it persists in our sky is because living organisms, from the smallest cyanobacteria to the largest forests, continuously replenish it through photosynthesis. Pair oxygen with methane, another unstable gas often produced by microbes, and you have a chemical imbalance that strongly suggests something alive is at work. Astronomers now aim their telescopes at distant exoplanets, studying the faint light filtering through their atmospheres as they pass in front of their stars, looking for these imbalances, for whispers of biology etched into the spectrum of light. Yet, biology may not always look like Earth's. Life elsewhere might use different chemistries, leaving behind signatures we do not yet recognize. That is why some scientists focus instead on techno-signatures, evidence not just of life, but of intelligence and technology. Since the 1960s, the search for extraterrestrial intelligence, or SETI, has scanned the skies for narrow-band radio signals, artificial pulses that could cut through the cosmic background. The silence so far has been profound, but silence does not mean absence. It could mean civilizations use communication methods we cannot yet detect, lasers, neutrinos, even gravitational waves, or it could mean they are deliberately quiet, cautious of revealing themselves in a universe that may not be friendly. The zoo hypothesis suggests we are being watched, but deliberately left undisturbed, like animals behind glass. The darker idea of the dark forest suggests that civilizations hide because to announce oneself in the cosmos is to invite danger. Either way, the lack of signals is as mysterious as their potential presence would be. Closer to home, the search is far more tangible. Mars, once flowing with rivers and lakes, may still hide microbial life beneath its surface. Rovers scour its soil, drilling and analyzing, searching for fossils or chemical traces of organisms. Moons like Europa and Enceladus, with their subsurface oceans kept warm by tidal forces, are prime targets too. Plumes of water erupt from Enceladus, venting into space, and missions are being planned to fly through those plumes, testing for organic chemistry or even microbes. Titan, with its methane lakes and thick atmosphere, offers another possibility, a world so alien that life there might operate on chemistry entirely different from our own. Each of these nearby worlds is a candidate, each one a reminder that we do not have to look light years away to find other biology. It might be hiding right here, in our cosmic backyard. The implications of even the smallest discovery are staggering. To find a single microbe on Mars, a fossilized cell, or even a hint of alien metabolism would mean that life is not unique to Earth. It would mean that, given the right conditions, life emerges naturally, perhaps inevitably. It would transform our view of the universe from a place of emptiness to a place of abundance. On the other hand, if after decades of searching we find nothing, the silence takes on new weight. It would mean Earth truly is special, that life is a rare accident, and that the responsibility of preserving it is infinitely greater. In either case, the search changes us. At its core, the search for life is not just about microbes or signals. It is about what their discovery would mean for us. If life is common, we are part of a grand cosmic family. If life is rare, then we carry a responsibility no other species has ever borne, to protect and nurture the only known spark of awareness in an otherwise silent universe. And that realization, whichever way it turns, may be the most important discovery humanity ever makes. In 1961, an astronomer named Frank Drake sat down to wrestle with a question that had haunted humanity for centuries. How many intelligent civilizations might exist in our galaxy right now? Instead of speculating wildly, he tried to structure the unknown. The result was the Drake equation, a deceptively simple string of variables that multiplied together to produce an estimate. It asked, how many stars form in the Milky Way each year? What fraction of those stars have planets? Of those planets, how many are Earth-like, orbiting in the habitable zone? Of those, how many actually develop life? How many of those evolve intelligence? How many intelligent civilizations develop technology capable of communication? And finally, how long do such civilizations last before disappearing? Each variable represents a chasm of uncertainty, yet together they form a framework, a way to turn wonder into science. Depending on the numbers you feed into the equation, the result can be as low as 1, that 1 being us, or as high as tens of thousands of civilizations scattered across the galaxy. At first glance, the optimism seems justified. Stars form constantly, and we now know planets are common, with Earth-sized ones not unusual at all. Even if a small fraction of those planets fall into habitable zones, the sheer scale of the galaxy, billions of stars, suggests that life should have had many chances to emerge. And if life began here on Earth quickly, within a few 100 million years of the planet cooling, perhaps it arises easily elsewhere too. By this logic, intelligence may be rare but not unique, and the galaxy should be buzzing with civilizations. And yet, when we look outward, we see nothing, no signals, no megastructures, no obvious signs of intelligence. This contradiction is known as the Fermi paradox, named after the physicist Enrico Fermi, who once asked a simple, devastating question: if the galaxy is full of life, where is everyone? The silence is haunting. One possible explanation is that intelligent life is exceedingly rare, that the jump from simple cells to complex beings capable of thought and technology is almost impossible. Perhaps the universe is filled with microbial life, but intelligence like ours is a fluke, a fragile branch of evolution unlikely to sprout again. Another possibility is that civilizations do arise, but they do not last. Technology, while powerful, may carry within it the seeds of destruction. Civilizations might annihilate themselves through war, climate collapse, or mistakes with technologies they cannot control. If that is true, then the galaxy could be filled with the ruins of civilizations that lived briefly and brightly before vanishing. There are darker possibilities too. Some thinkers propose the Great Filter, the idea that somewhere along the path from simple chemistry to spacefaring civilization, there is an almost insurmountable barrier. We do not know if the filter lies behind us, meaning life itself is rare and we are one of the lucky few, or ahead of us, meaning that self-destruction awaits all advanced civilizations. The uncertainty is chilling, because the placement of the filter defines our fate. If it lies behind us, then we are unique and precious. If it lies ahead, then our survival is in jeopardy. But perhaps the paradox is not a paradox at all. Perhaps civilizations exist, but communicate in ways we cannot detect, using quantum entanglement, neutrinos, or technologies so advanced they are indistinguishable from nature. Perhaps they deliberately remain silent, fearful of broadcasting their presence in a potentially hostile universe, or perhaps the galaxy is too vast, and the timescales of civilizations too brief for signals to overlap. We may simply be too early, standing in a quiet galaxy that will one day be alive with voices, but not yet. Whatever the explanation, the silence forces us to reflect inward. The final variable in the Drake equation How long civilizations last does not just apply to aliens, it applies to us. Are we capable of surviving long enough to send our voice across the galaxy to endure for thousands or millions of years? Or will we be just another whisper lost to entropy? The Drake equation may not provide an answer, but it reframes the question. It tells us that whether the galaxy is full of civilizations or empty, our choices now matter profoundly. Either we are one of many voices waiting to be heard, or we are the only voice at all. In both cases, the responsibility is immense. As we reach the end of this journey through stars, galaxies, time, and mystery, one truth becomes impossible to escape. The universe is vast beyond comprehension, and our place within it is both fragile and profound. We began with the question of scale, of how immense space truly is, and along the way we uncovered stories of light and gravity, of galaxies colliding and stars being born, of dark matter and dark energy shaping destinies we cannot control. We explored the strange silence that surrounds us, the haunting absence of signals in a galaxy that should be full of life, and we weighed the possibilities of why we have not yet found companions among the stars. At every step we confronted not only scientific revelations, but emotional ones, the awe of knowing we exist in such immensity, the fear of our smallness, and the wonder that somehow, despite everything, we are here to ask these questions at all. The universe does not bend itself to human meaning. It does not promise us permanence or purpose. Galaxies spin, stars ignite, black holes devour, and expansion carries everything farther into the cold. If life exists elsewhere, it has so far remained quiet. If it does not, then every thought, every story, every act of kindness on Earth is infinitely more precious, because it may be the only expression of consciousness the universe has ever produced. That duality, possibility on one side, isolation on the other, defines our moment in history. We stand on a small planet, orbiting an ordinary star, in a quiet arm of a spiral galaxy, and yet from this unremarkable vantage point, we have measured the age of the cosmos, traced the afterglow of the Big Bang, and speculated on the ultimate fate of existence itself. The silence of the stars is not only a scientific puzzle, it is a mirror. It reflects our fears about survival, our hopes for connection, and our questions about meaning. If the great filter lies behind us, then we are rare survivors and must cherish our improbable existence. If it lies ahead, then our responsibility is to navigate carefully to ensure that we do not extinguish ourselves before we have the chance to reach the stars. And if the galaxy is full of civilizations who are silent by choice or invisible by nature, then our role is to decide what kind of voice we will be when we finally join the chorus. In the end, perhaps the greatest revelation is not about the stars, but about ourselves. We are made of the universe, hydrogen from the Big Bang, carbon from ancient stars, iron from supernovae, and yet we are more than the sum of atoms. We are awareness, fleeting and fragile, but capable of wonder, that capacity to ask, to imagine, to feel awe, when confronted with the infinite, may be the universe's most remarkable creation. The stars do not know they shine. The galaxies do not know they dance, but we know, and in that knowing lies significance. So the conclusion is not an answer, but an invitation. An invitation to keep questioning, to keep searching, to keep caring, not because the cosmos demands it, but because we choose to. If life is everywhere, then we are part of a grand story. If life is nowhere else, then we are its only storytellers, and that makes what we do here matter beyond measure. Either way, the weight of meaning rests not in the size of the universe, but in the size of our response to it. You are small, yes, but you are also rare. You are temporary, but you are awake. And in a cosmos that has existed for billions of years without awareness, that brief flicker of consciousness is everything. The universe does not give us purpose. It gives us silence, stars, and time. What we build from them, knowledge, kindness, beauty, connection, is ours alone to decide. Perhaps that is enough. Perhaps that is everything.